أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم السلام عليكم ورحمة الله وبركاته. Thanks to Allah subhanahu wa ta'ala for all His blessings and bounties that He has bestowed upon us. فَبِأَيِّ آلَاءِ رَبِّكُمَا تُكَذِّبَانِ. More or less meaning, which of the blessings of your Lord will you both jinn and insan deny? So we need to make sure to Allah subhanahu wa ta'ala who has created us as a mankind, the best of all the creations, the Ashraful God. Alhamdulillah, Alhamdulillah. Alright, so we look into our today's lecture. If you remember in the last lecture, we have completed to some extent one particular topic, differential equations. Started off with the idea how we describe a differential equation. And then got different techniques to simplify them for first order as well as higher order. And then on top of that, we have gone through with few of the applications, most vital applications available in the literature. Today we are going to talk about Laplace Transforms. What the transformation is? It's a simple word, literally meaning the transformation. You transform a function or an equation from one state to another state. We change the course of the function or equation from one state to another state. So what the purpose is there in mathematics for these kind of transformations? Laplace is not the only transformation. We have quite a few. But this is going to be one of the vital. Why so? We will look into that in a couple of minutes. We say that in mathematics, transformation means we are interested to reduce certain problems which we are unable to simplify them or which are going to be very difficult to solve. So we transform, we are interested to transform those problems which we cannot simplify or which are going to be difficult to simplify into corresponding problems which are relatively easier to solve. So, like a bridge between two different states, between two different kinds. So we will be having sort of transform. So we will transform the course of function and equation from one state to another state. That's the purpose behind the scene. That's the objective behind the scene. What the Laplace transformation is, we say that the method of Laplace transform is one of the efficient methods. It's not the only one. Quite a few are available in the literature. We will also look into Fourier transformation later in this particular course. So Laplace transformation is going to be regarded as one of the most efficient one. So remember, accuracy and efficiency, they are vital to be discussed whenever we talk about the computational cost, whenever we look into the quality of one numerical technique, one numerical method, or one method, whether it is numerical or analytical. Analytical one is the method which gives us analytical solution, the exact solution, whereas Numerical methods, they always provide us approximate solutions. So whatever the method is there, whatever the technique is there, we have to quantify the quality of the technique. How do we observe the quality of that technique? By looking into the error. Smaller the error, the better the accuracy produced by that numerical technique or that analytical technique. So accuracy means how our obtained solution is going to be closer enough to the exact solution when we talk about the numerical solution in particular. So this is how we look into the accuracy. In other words, we could say that up to how many decimal places, when we talk about the numerical values, up to how many decimal places our numerical solution does agree with the exact solution. From there, we observe the degree of accuracy. I mean, up to how many decimal places, the exact and approximate solutions, eventually they do agree with each other. Whereas the efficiency is on top of accuracy. If there is only one method, we can't talk about the efficiency. Remember, it's very vital to be understood. If there is one method, we can't talk about its efficiency. We can talk about its accuracy. Yes, it's an independent one. But when we talk about the efficiency, you have to have at least more than one. So assume that we have two numerical methods behind the scene. So we fix the accuracy barrier. Both methods, they attain the same degree of accuracy. And then on top of that, the one which takes less computational cost is going to be the efficient one. So for efficiency, you need to set the barrier of accuracy. So as an example from our daily life, for example, you want to run a race between two vehicles. One has got 4 perfect wheels. The other vehicle has got 3 perfect wheels, and one of the wheel is not in that perfect form. It's somehow damaged. One vehicle with 4 perfect wheels, the other one 3 are perfect, and one is contaminated, one is damaged somehow, and you want to run a race between them. Is it going to be a fair race between them? Surely not. It is pretty obvious. The one with 4 perfect wheels is going to win the race. So this is not going to be the efficiency. You can't count the efficiency in that particular fashion. Yes, both vehicles have got 4 perfect wheels. They are on the course, and then you can run a race between them. Eventually, you see the one which takes less time to complete the race is going to win the race. So we say that yes, this one is that much efficient. So efficiency is on top of accuracy. First of all, you need to set the accuracy barrier, and then we see the one which takes less computational cost is going to be the efficient method. So computational cost at the high level, what we observe, the parameters behind the scene for efficiency, we observe the efficiency in terms of number of function evaluations. I mean, how many times the derivatives are computed through one particular simulation. Because derivative is going to be computationally a bit costly to calculate. So we observe the computational cost in terms of number of derivatives evaluated during one particular simulation. Our second parameter is the CPU time, the time it takes the computer to complete one simulation over a specific period of integration, maybe for example, for 1,000 years, 1 year, 1 month, by taking a step size of 1 day, for example. So this is all. These are the parameters. But normally, at the small level. What we observe, the efficiency, we observe the number of steps being performed, the number of operations being performed, the algebraic operations, addition, multiplication, subtraction, and division. Based upon those operations, based upon those steps, normally we observe the efficiency. So we regard Laplace as one of the efficient methods for solving linear differential equations and corresponding initial and boundary value problems. So there are quite a few, but since this one is regarded as the efficient one, so this is all we prefer to look into the implementation of Laplace transformation when we are interested to solve linear differential equations. And since we know that if a problem is there, together with certain conditions, if the conditions are initial conditions, the problem is going to be initial value problem. And if the conditions are boundary conditions, then the problem together with the conditions is going to be boundary value problem. The difference between initial and boundary conditions is that if all the conditions are subject to only one value of the independent variable, then the conditions are known as initial conditions. Like y of 0 is equal to 1, y prime of 0 is equal to 1. So you see that y means the position is available for the independent variable's value 0. Velocity is also available for the same value of the independent variable 0. So we have two conditions, but they are all subject to only one value of the independent variable 0. So we say that these are the initial conditions. On the other hand side, if the conditions are subject to more than one values of the independent variable, we say that these are the boundaries. So just like, for example, y of 0 is equal to 1 and y of 1 is equal to 2, for example. So y of 0 and y of 1. So it means that 0 and 1 are two different values of the independent variable. So just map on the real line, 0 is there, 1 is there. So you have sort of boundary over there of that much length. So this is all. The conditions are going to be boundary conditions. The problem is there with the conditions, either initial or boundary. So they are going to be initial value problem or the boundary value problem respectively. So we normally what happens when the conditions are initial conditions, the differential equation behind the scene is going to be ordinary differential equation. Normally, it's not the fundamental rule behind the scene, but generally what happens, initial conditions are generally associated with ordinary differential equations, whereas boundary conditions are associated with partial differential equations. We haven't discussed that. We'll look into that in the next topic, partial differential equations. So partial differential equations together with boundary conditions, so they will make boundary value problems. Ordinary differential equations together with initial conditions, they will make initial value problem generally, not the hard and fast rule. Some cases are there where we could have boundary conditions together with ordinary differential equation, vice versa. But generally what happens, we look into that. So it means that since we have discussed about the ordinary differential equations, so we will more look into the initial conditions together with the ordinary differential equations to make them initial value problems. So basically, please mute your microphone, all of them. So let me double check. And ensure that all of them are muted. Okay, yes, it's done now. All right, so what the message is there behind the scene about this Laplace transforms method? We say that it's a transformation, it will change the course of problem from one state to another state, from a difficult state to an easier one, relatively easier one, so that we can look into the solution. There are four components behind this scene, starting from the problem to the last step, being the solution of that problem. So we will look into that. So basically, this method reduces the problem. So this is the description of four compartments, four components of this technique to be implemented to get the solution of the given differential equation. So what the message of this method is, basically this method reduces the problem of solving a linear differential equation into an algebraic equation. So we have differential equation and we reduce into the corresponding algebraic equation. Differential equation does involve derivatives up to certain order, whereas the algebraic equation is the one having no derivatives, free from derivatives. An equation is said to be algebraic if there is no derivative in it. So it's a simple expression like x squared plus 2x plus 3 is equal to 0. It's an algebraic equation. Equation is there because of the equality sign, and then simple algebraic expressions are utilized without any derivatives. So remember, there are quite a few types of equations: differential equations, algebraic equations, integral equations. Plenty of types are there. So we will transform our differential equation into the corresponding algebraic equation, whose solution, the solution of algebraic equation. So it's much easier, no? You see that if there is an algebraic equation, we can easily look into the solution of that algebraic equation by using those usual methods available in the literature. We have gone through, even in the matriculation, we go through with a couple of those methods for the solution of algebraic equation. Sometimes if it is only one equation, very easy to handle that particular equation. So targets or the message is there: differential equation is going to be reduced into the corresponding algebraic equation. Then we will find the solution of this algebraic equation by using usual algebraic methods. And then the inverse of the Laplace, known as inverse Laplace transform, will take us back to the solution of the given problem. Problem is differential equation. So our target is to find the solution. What we do, we change the course of this differential equation into algebraic equation. We find this. So first step, change the course of differential equation together with certain condition if there are initial. So we assume that there will be initial value problem. So it is changed or reduced into the algebraic equation. First step. Second step, find the solution of algebraic equation and then take the inverse of the solution for algebraic equation. Now that solution will basically take us back to the solution of the original initial value problem. So this is the message of this Laplace transformation is: change the differential equation to algebraic equation, find the solution of algebraic equation, and then that solution will take us back to the solution of the original problem by taking the inverse of Laplace. So initially, we will try to look into the half of the part, the transformation from initial value problem to Okay, sorry for that. So because of the network quality at that time, I have some troubles. Okay, is it visible to you, all of you again, the screen? If one of the CR, I recommend one of the CR respond.
Yes, sir.
All right, thanks. So the flow chart or the schematic that will illustrate the method of Laplace transform. Okay, again we have to utilize whiteboard, which is going to be a demanding task. Last time we did that. Anyway, what would be the other option? Microsoft Paint. Since I'm using Mac is an operating system other than Windows. So remember, there are quite a few. Linux is one of the operating system. Windows is another operating system. Mac is also an option behind the scene. I have a Mac. So there is no Microsoft Paint. Uh, we will have to look into the alternative one because once we look into the whiteboard, my MS Teams whiteboard, so I don't have control over there. So I give you an idea. So you can try yourself. Make four boxes. Box number one, and then an arrow to the right. Second box. Take a pencil and a piece of paper. So make four boxes connected with each other. To the extreme left, make a box. And then arrow connected with the second box to the right of the first box. Then another arrow connected to the right with third box. And finally, one more arrow to the last box connected with all. You try to have four boxes. Box number one, then little bit space with an arrow. Second box, one more arrow. Yes, please.
सर ये थ्योरी शो हो रही है, आपने अगर कोई फ्लो चार्ट शो करवा रहे हैं तो वो नहीं हो रहा स्क्रीन पर, थ्योरी शो हो रही है.
I'm describing that. So try to note down the illustration.
उस पे सही हो जाता है ना.
Is it possible? This description is going to be illustrated. This description, I mean, this second to last, or the combination, the second to last paragraph, the sentence in the last paragraph, the description of that. Four boxes will be there, connected with each other from an arrow. So
Sir,
in the
Google
yes,
Jamboard खोल.
Sorry, say again.
Sir, Google Jamboard.
Google Chat.
Jamboard. Chat box देख रहे हैं उसके अंदर.
Sorry, I'm not familiar with that. Okay, what can we do?
Sir, you can use Microsoft Paint if you want and share the screen. That will be very easy, and students have no control over that.
But I don't have Microsoft Paint because I'm using Mac. There is no such facility in Mac.
Sir, there will be an image editor in Mac also. You can use that.
Because you people are using Windows, I believe, isn't it? It's a different operating system, slightly different.
Yes, sir, but there should be an editor in Mac also to edit pictures, etc. You can use that.
Editor. Okay, I will have to look into that.
Sir, I have sent you a link for online paint. If you look in the chat box, I have sent in the link.
Sorry, say again.
I have sent you a link in the chat box for an online type paint or whiteboard, if you can say.
Okay, let me see. Technology is very important for human being, but sometimes there could be a problem with the technology. So I feel that the internet quality is not that. So this is a little bit difficulties there behind the scenes. Jamboard, Google Jamboard.
अस्सलाम वालेकुम।
वालेकुम अस्सलाम।
एक मिनट जरा। हाँ जी, रक्षे वाले से बात हुई थी, क्या कह रहा? मामू आपकी आवाज़ सही तरह नहीं आ रही है मेरे। किन्ने सही तो मामू का नंबर दे रहा मैं आपको करना।
Yes. All right, again, yes, it is there. Is it visible now? Again, the screen. CR.
Yes, sir, visible.
All right. So I was saying that make 4 boxes. First box. And then an arrow, for example. And over here, another box. An arrow is there. The third box. One more arrow. And the last box. So this is all. We are having 4 boxes. They've been connected with each other. So in the first box, you need to write it down. Initial IVP, capital I. IVP. So you need to fill the first box with I, V, P. Capital I, capital V, capital P stands for initial value problem. And then above this arrow outside the box, write it down this symbol, the small curly L. Small L. It's a specific symbol for Laplace transformation. So in the first box, initial value problem, small symbol, small L. Specific symbol you will see in the lecture, this particular symbol for Laplace transformation. In the second box, algebraic problem. Initial value problem is here. Write it down here. Algebraic, A-L-G-A-B-R-A-I-C, algebraic problem. And the third box, solution of algebraic problem. And finally, solution of the initial value problem. So again, I repeat this schematic. Sorry for that, because this is not the best of the way. Anyway, we have 4 boxes. They've been connected with each other. So the very first box, inside the box, IVP, initial value problem. Then this is the symbol, small l, is the symbol being utilized for Laplace transform. So Laplace transform will reduce this initial value problem. In the second box, inside the box, write it down, algebraic problem. So algebraic problem is there. The next step would be to find the solution of this algebraic problem by using those usual algebraic methods. And finally, inverse of L means inverse of Laplace will take back to the solution of the given initial value problem. Our target is to find the solution of initial value problem. Since it's difficult or we cannot find the solution, we will reduce this one to algebraic with the help of Laplace. From algebraic, we will find the solution of algebraic equation. Since this solution is corresponding to the algebraic in the third box, and we are interested to find the solution of the given initial value problem, so we have to utilize the inverse of that. That inverse will take back to the solution of the given initial value problem. All right, so we move on. So this is all. I mean, this is the illustration. Some pictorial representation or graphically, or we look into the description of the method. For example, now we'll take certain examples. For example, what the definition is there. For example, we have a function f of t. Function is real valued. It is not going to take us to the complex numbers. Real number is going to be the second to last, or every number other than the complex is going to be regarded as real. So function is real valued and it is defined full sort of values of t greater than or equal to 0. I mean, we are talking about the right half of the real line. Real line is extended from minus infinity to infinity. So we talk about half from 0 to the right. Full sort of values of t greater than or equal to 0 is multiplied by e raised to power minus st and then integrated with respect to t, because it's a function of t. So the variable of integration is going to be t from 0 to infinity. So once this function is multiplied by e raised to power minus st and then on top of that integrated from 0 to infinity, a new function of the variable s, say f bar of s, is obtained, where s may be real or complex. We are not bothering about that. Generally, it is going to be real. The function f bar of s is called the Laplace transform of the original function f of t. So original function is f of t, and we transform into another one, f bar of s, which is known as Laplace transform original function f of t, and is denoted by, so this is the symbol. Yes, we are back. All right. So this is all the definition is there. We will be having an f of t, and we are interested to apply Laplace. We are going to transform this function. Still, remember, our target is to talk about initial value problem, but we are going to talk about the basic stuff. How we take start talking about the definition, and then eventually we will talk about differential equations. This is the ultimate objective of the Laplace transformation. So what the definition? We will be having f of t, which is defined full sort of values of t greater than or equal to 0, and the output is going to be real valued function. So what the definition? This function is multiplied by e raised to power minus st and then integrated over the interval from 0 to infinity with respect to t, because this is going to be the variable of integration as a dummy variable. So once we do that, eventually out of that there will be a function of s. So we label it as a symbolic representation f bar of s. So this is the definition. If you are interested to find the Laplace transform of a real valued function f of t, so you need to plug in over here whatever the expression of f of t, multiply it with e raised to power minus st, then integrate with respect to t over the interval from 0 to infinity. The outcome is going to be the corresponding reduced form or the transformed version of the original function f of t. So f bar of s will be there. So this is all, the definition is there. Noted that the variable of integration t is a dummy variable and can be replaced by any other symbol. I mean, whatever you like. But generally, what happens in the literature, people would love to utilize t as a dummy variable. The process of finding the Laplace transform of a function is called Laplace transformation. Just like the integral is there, and the process is known as integration. The derivative is there, and the process is known as differentiation. So the process of finding the Laplace transform of a function is known as Laplace transformation. Prove that the Laplacian operator, that symbol, curly L is a linear operator. That is, if C1 and C2 are any arbitrary constants, f1 of t, f2 of t are any two real valued functions whose Laplace transforms exist, then we say that Laplacian operator is a linear operator, just like the property that we utilize in the case of a limit, just like the property for the differential operator. We do separate the terms. So pretty much on the same line, we have the first term, C1 f1 of t. C1 is a constant value plus C2 f2 of t, and we need to apply the Laplace on that combination. So what we see, we can separate them. C1 is taken outside because it's a constant value. Laplace of f of t, f1 of t plus C2 times Laplace of f2 of t, should be f2 of t. It's a typographical error. And then what is this? As a symbolic representation is f bar of 1 of s, and the second one is basically f2 bar of s. So it's a typographical error, f2. So Laplace of the combination of two functions will be the Laplace of those individual terms, and eventually we will be having C1 f1 bar of s plus C2 f2 bar of s. So we need to show that yes, we can separate them, and eventually we will be having Laplace as an output, Laplace function for those individual f1 of t, f2 of t. So by definition, what we see, definition states that if you go back and have a definition, Laplace f of t. So f of t is to be multiplied by e raised to the power minus st and to be integrated over the interval from 0 to infinity with respect to t being the variable of integration. So that's what we do. Whatever is there inside the bracket, so we assume that this is going to be 1 unit. So by definition, it has to be multiplied, this whole combination, by e raised to the power minus st to be integrated over the interval from 0 to infinity with variable of integration. So this is all. The expression is a complete expression. And then we know the property. So we can multiply this one to each term, and then they could be separated. This integral sign could be separated for both of them. And what is this? If you carefully look into that, this whole thing, and keep an eye on the definition, e raised to the power minus st from the formula, dt with the integral. Integral is a 0 to infinity. So f of t is going to be labeled as f bar of s. Whatever is this is going to be implemented. So it's f1 of t. So it's basically Laplace of f1. So yes, this whole thing. And you can also say that it's basically f1 bar of s. And the second one, this is basically the Laplace of f2 of t. The Laplacian operator is there. So for this one, you could also say that this is f2 bar of s. So yes, pretty simple proof. Only a couple of lines are there. And it will prove that yes, we can separate, just like we separate the integral sign for each term, just like we separate the differential, it's just like we perform limit, many other things are there. Pretty much on the same line, we can say that this operator, the Laplacian operator, is also linear operator. We can separate those terms. Now we look into the Laplace transforms of some of elementary functions. For example, if there is a constant, what will be the outcome? We will show that the Laplace of a constant value is c upon s, because it has to be, the outcome has to be function of s. Whatever the constant is there, for example, 1 is there, so it will turn out to be 1 upon s. If c is equal to 2, so it will turn out to be 2 upon s, because it has to be function of s as an output. So where s should be positive. Because by definition, S has to be positive, because if S is negative over here, this could be taken into the denominator, e raised to power st with upper limit as infinity. You don't have a finite value over there. So it is only possible if the exponent is going to be negative. Only then it can be taken into the denominator. Otherwise, if S is negative, so negative into negative positive, so e raised to power positive infinity will take you to infinity. And because of the negative sign, we bring it into the denominator. 1 upon infinity is going to be 0. So this is how we apply the phenomenon. So as a precautionary measure, S should be positive. All right, we are interested to find the Laplace of this constant. By definition, Laplace of any function is going to be integral from 0 to infinity, multiple of e raised to power minus st with variable of integration t. So c is constant, taken outside the integral, integrate this one, apply the upper limit and the lower limit, eventually it will turn out c upon s. Simple proof is there, but the formula is there. You need to keep an eye on the formula, because eventually you need to utilize those formulas directly without going into the proof. So the first formula is there. Laplace of any constant is going to be that constant upon s. So second, we will have to look into Laplace transform of trigonometric functions. Laplace of sine of at. The outcome is going to be a. Remember, a is multiple of an angle upon s square plus a square. Instead of sine, if it is cosine, so only the numerator is going to be changed. I mean, this is how you can keep an eye or memorize those formulas. Eventually, you have to. For sine, it's a upon s square plus a square. For cosine, it's s upon s square plus a square. So take the first one. By definition, we know what the formula is there behind the scene. But before we move on, we could also utilize the first result. We have gone through that. Or have we gone through that? So there are more than one version basically to go down with the Laplace transform of sine of at and cosine of at, because they could be combined together as a complex value. But anyway, we look into the individual one. Laplace of sine of at. So sine of at could also be described in terms of exponential function e raised to power iota at minus e raised to power minus iota at upon 2 times iota. This is the relation, the trigonometric relation, sine of at from the previous classes, e raised to power iota at minus e raised to power minus iota at upon 2 times iota. 1 upon 2 times iota can be taken outside because of the linearity property. We can separate the Laplace transform of the first and the second one. Okay, we should have proved the Laplace transform of exponential function before we talk about sine. Anyway, it's not done, but keep an eye on the formula. So the Laplace transform of e raised to power at is basically 1 upon s minus a. We haven't proved that, but you can also look into that, just like the constant is there. So e raised to power at Laplace will be equal to 1 upon s minus a. So e raised to power iota at Laplace is going to be 1 upon s minus a. A is multiple of iota here. So minus. So Laplace of e raised to power minus iota a. So 1 upon s minus this thing, multiple of t. So minus into minus plus. So this is a plus iota a. I mean, you can give an idea that the Laplace of e raised to power, later on we see this one in the table, that the Laplace of e raised to power at will be 1 upon s minus a. A is multiple of t in the exponent. So plug in the Laplace transform of this exponential function for the second term by taking 1 upon 2 iota common and then simplify. Simple algebraic expression is there. Once you do that, so eventually it will turn out to be a upon s square plus a square. Couple of steps you need to perform that. So in this way, you can prove that yes, the Laplace transform of trigonometric function would be equal to sine of 80 in particular, a upon s square plus a square. Laplace of cosine of 80 s upon s square plus a square. Remember, if you know sine and cosine, rest of the four could easily be obtained, like the Laplace of tan, it is going to be the fraction between sine and cosine, cot is the reciprocal, secant is the reciprocal, cosecant is also the reciprocal. So all those remaining four trigonometric functions, they are based upon sine and cosine. So if you know an expression for sine and cosine, the rest of them could easily be obtained from them. Laplace transform of hyperbolic functions. Sine hyperbolic 80, a upon s square minus a square, s upon s square minus a square. So what we have done, remember, sine of 80, a upon s square plus a square, s upon s square plus a. Denominator is identical, only the numerator is going to be changed. So the difference between the Laplace of sine 80 and the Laplace of sine hyperbolic 80 is that negative sign, remember. A upon s square minus s square. There is a warning, of course, as a precautionary measure. Constraint is a upon s square plus a square for sine and a upon s square minus a square for sine hyperbolic. We started off with this expression, remember. For sine 80, the expression is e raised to power iota 80 minus e raised to power minus iota 80 upon 2 iota. When we talk about an expression for sine hyperbolic 80, it would be e raised to power 80 minus e raised to power minus 80 upon 2. So get rid of iota basically. I believe this would be the expression for sine hyperbolic 80, and then the rest of the process is pretty much identical. You can try this one, the first one, pretty much on the same line, just like we have done this one. Use the Laplace of e raised to power 80 as 1 upon s minus a. You try yourself this one. In the meanwhile, I generate a poll for you people. Attendance 8th of July 2020. So we are in the CBC present. And here you go. So I have created a poll for you people for attendance purpose, so do mark it. All right, so we move on. Just like the Laplace of sine of t is a, you would be able to find an expression for the Laplace of sine hyperbolic, because eventually you need to memorize those formulas. You don't want to go back and then complete the procedure by using the definition over and over again. So this is all. We are interested to memorize those formulas for those well-known expressions, like exponential function is there, trigonometric functions are there, sine and cosine are good enough, constant function is there, and the last thing is a polynomial of certain degree. Polynomial of certain degree, like t raised to power n. What would be n? 0. If n is 0, it is going to be a constant value. And remember the formula. What was the formula? C upon S. So if n is 0, 0 factorial is 1, 0 plus 1 is 1. So 1 upon S in the case if n is 0. So it's basically the justification of the previous one. So t raised to power n is going to be generalized case for any value of t. If n is equal to 1, so 1 factorial upon s raised to power n plus 1 means 2, or 1 upon s raised to power 2. If n is equal to 2, 2 factorial means 2 divided by s raised to power 3. So this is all. The direct outcome is there if we have a polynomial of certain degree. So how can we prove this one? We can look into the proof by using the method of induction. You must have gone through that in the matriculation, I believe. For 0 and then for any value of k, and then eventually justify that one for the case of k plus 1. Eventually we will say that yes, it is going to be for all non-negative integral values of n. We know integers are there, positive 1, 2, 3, negative minus 1, minus 2, minus 3. 0 is neither there to the positive or negative side. But yes, when we say non-negative integers, 0 is going to be added into the right part. 0, 1, 2, 3. So these are non-negative integers. So you can prove this one. Otherwise, it's there in the literature. You can have a look at the proof, or you can also look into the proof yourself. Try yourself for all the values. Start by taking n is equal to 0. So n is equal to 0 will take back to the original function, like c is there. So 1 upon s will be the outcome. We have gone through. Yes, Laplace of any constant is constant divided by s. So if n is 0, so it will turn out to be t raised to power 0 means 1. So 1 constant. Laplace of 1 is 1 upon s raised to power 1. So it will automatically be verified for n is equal to 0. And then you can look into the generalized case for 1, 2, 3, 4 by taking into consideration k, and then the justification is done by k plus 1. This is all the method of the induction method is implemented for all non-negative integral values of n. So we summarize the formulas in the form of table. So that's what we have now. We started out with a description of Laplace transform, what the message is there. Laplace is going to be one of the efficient options behind the scene for initial value problems. We got an idea about the definition, and then we discussed few of the functions and their Laplace transformations. So are done in few of the examples. So if the function is constant like 1, so what the outcome is there by using the definition, it will turn out to be 1 upon s. If f of t is t raised to power 1, so 1 upon s raised to power 2. If it is t square, 2 is there, so 2 factorial means 2 divided by s raised to power 2 plus 1 means 3. And this is the generalized. If you just keep an eye on this formula, all previous are going to be covered inside this formula number 4. Whatever the value of n, you can get the outcome. We rarely utilized number 5. It's a gamma function. Gamma is closely resembled with the definition of Laplace gamma function. At the high level, we do utilize. If we have in the upcoming slides certain example where we do need to utilize gamma function, so keep an eye on the formula. We haven't gone through with the formula. We haven't gone through with the proof of that one. Otherwise, it is going to be like that. So you see that for t raised to power n, it's n factorial. So n factorial is basically gamma of n plus 1. The rest of the part is identical, denominator, s raised to power n plus 1. This symbol stands for gamma function. It's an additional component. Number 6, Laplace transform of e raised to power at. A is going to be a constant value. So 1 upon s minus a, with the condition, of course, is the sine of at. Yes, we have gone through that. Cosine of at. Yes, we have gone through that. Sine hyperbolic. So the only difference between sine at and sine hyperbolic at is the sign in the denominator, plus and minus. Much easier to memorize those formulas, remember? Corresponding to sine 80, we have sine hyperbolic 80. Corresponding to sine 80, pretty much the same formula, only the difference is sign in the denominator. For cosine, it's positive. For cosine hyperbolic, it's a negative sign. So this is the table for all sort of formulas. Mostly we do utilize in the case of Laplace transform. So by utilizing them, you can look into the implementation, find the following Laplace transforms. Laplace transform of a times e raised to power bt, where a and b are constants. Utilize the formula from the table. Laplace of a plus bt plus ct square, it's a polynomial, 0th degree in the first term, degree 1 in the second term, degree 2 in the third term. So first of all, do separate them, because linearity property does hold for Laplacian operator. So separate them, Laplace of a plus Laplace of bt plus Laplace of ct square. Then Laplace of a constant a is going to be that constant divided by s. For the second one, take this constant outside and then look into the Laplace of t. We know is going to be 1 upon s square. So eventually it will be b upon s. Same is the case, you can try to get down the expression for Laplace of ct square from the table. So I believe it will turn out to be 2c upon s cube. So this is all. The expression would be there. Corresponding to f of t, there will be a function with variable s, f bar of s. So Laplace of 6 times sine of 2t. So in the table, we had a. Now it is going to be 2 in both cases. First of all, separate them. Laplace of 6 sine of 2t minus Laplace of 3 cosine of 2t, and then take those constants outside. Then Laplace of 3 cosine hyperbolic 5t, and Laplace of sine hyperbolic of 5t. So you can try these few examples. At the beginning, of course, you need to memorize those formulas. In the upcoming lecture, of course, we will only utilize those formulas from the table. Most of the expressions are there in the table. You can directly take them. If it's a constant value, polynomial of certain degree, exponential, trigonometric, or hyperbolic functions are there. So we need to keep an eye on those outcomes, the right side. So we have to utilize them corresponding to the given expression. So the direct implementation will be done instead of going back and then performing all the definition, the hard working behind the scene, we will utilize those outcomes directly. All right, so that's it. We got some time. If you have any query, we can look into that.
Excuse me, sir. Can you please tell us when the university is going to be opened again?
I'm not sure. It has to be done by the administration inside the university. So they are looking into the instructions given by the Higher Education Commission, particularly, or by the Chancellor, the Governor of Punjab. Scene is not clear yet. We are expecting that before the final examination, we might be in the classes again. But it's it's not sure. I'm not giving any statement about that. We are expecting. We are hopeful that it will be. Okay.
I'm asking because, sir, teaching differential equations from online classes is sir, not something good in my opinion, because it's very difficult to keep up with the pace. Because, sir, a lot is happening behind the scenes. We, sir, can't just learn everything we see from the screen. We have to give it time. We have to be in front of each other to interact, so we understand it.
Yes, I acknowledge that. What are we trying to do? Something is better than nothing. Something is better than nothing. That's what we are looking for. And we try our level best to do it in the best way as possible. But of course, this is not the same scenario. This is not the same environment that we had in the classes. Live presentation is there, live conversation is there, demonstration is done on the board, slides are there, description is there, verbal conversation was there. So many things positive were happening in the classes. Due to the unfortunate circumstances, so that's what we have. Otherwise, we can't do anything. So we are basically looking into something better than nothing. That's what I could say.
Okay, sir.
No, it's an individual effort. Of course, you need to put more effort than me in learning those tasks behind the scene. But of course, it's not the ideal scenario, but you need to put more effort. Yes, if you have any query, you can get back to me by email. I will try to get back to you. क्या इसी तरह सेमेस्टर हमारा सेमेस्टर समथिंग के साथ ही कंक्लूड होगा? Not sure about that. It's not in your hand. It's not in my hand. So who knows? Who knows? Who knows? Something is better than nothing.
Excuse me, sir.
Yes, please.
What about the dummy variable?
Dummy variable, you could replace t by another variable. For example, if you do that, it won't affect the process of integration. It won't affect the outcome. Yes, please. '81. About the quiz, about the examination, we are still waiting for the instructions by the administration. So once we get, so they will be passed on to you. So we have to wait and see. Online classes can just give us burden and stress. What kind of stress, man? Come on, you are sitting in your drawing room, in your bedroom, enjoying your life, isn't it? And number 9, try to be relaxed with your family. Yes, Mr. Javed. Poll is there. Poll is there. Poll has been created, Mr. Javed. You can talk to CR of your section for assistance. Learning in person, face to face is much better. Yes, I agree with that. Absolutely agree with that. Since at present we can't sit in the class, SOPs to be defined. They are going to be set before we sit in the class. Might be, I mean, we have to cut down the strength of the class. This is another possibility because somewhere discussion is in progress that there might be at maximum 20 to 25 students in the class. So this is all they could have the social distance between them. Sitting arrangement would be such that the people could sit at a certain distance from one another. And in this way, because of the dimension of the classroom, people could be at maximum around 20-25, for example. Yes. This is another phase, of course, spending time on laptop. This is another phase of life, so we have to adjust ourselves. So try to adjust yourself. I mean, this is the blessing of Allah Subhanahu wa Taala, who has made this mankind, the body of the mankind, in such a way that it could be adjusted accordingly. So you can just try to do that. In the classroom, the classroom will be closed area and the virus may be in that room. You can't provide any sort of guarantee, of course. It's not visible to everybody, so you can't say anything about that. Might be there, might be on the road, might be in the street, might be inside the house where we are living. So can't say anything about that. Where it could be, and if it's there, I mean, different theories are there. It is possible that you might be affected by that virus already, but you didn't know that. And you have already been cured of that. This is another possibility, that you were affected by the virus without knowing that, and eventually got cured of that without any intimation. It's another theory behind the scene. All right, if there is any serious query, we can look into that. Otherwise, thank you very much. Have a nice day. See you inshallah. Assalamu alaikum wa rahmatullahi wa barakatuh.